Hi everyone, this is lecture 18 and we're continuing with our study of pairs of random variables. In particular, our focus is on continuous random variables x and y. And to end last class, we were working on problems where there's a region A and we're interested in the probability of A, which is just shorthand for the probability that the XY pair belongs to a region A. And the theorem says this is just the integral over the region A of the density. And if you recall, the PDF times dx dy is telling you the probability that x is between x plus dx and y is between y plus d. For example, suppose A is the set that x is between 0 and 1, and y is between 0 and x. In that case, the region looks like on the xy plane, we have to label the axes, and we have to be in the upper right quadrant since x and y are both positive. And then here's the line where y equals x. This is the line y equals x, and this is x equals 1. And the region of interest is all of this stuff. Because in this region down here, y is less than or equal to x. The rest of this problem is simply calculus. For instance, you would set up this integral where x goes from 0 to 1, and then the inner integral, y, is along this segment. For each x, y goes from 0 up to x, and then you would have the joint PDF, and then you would have the integral dy, and if you'd be very specific, you would write dx. And the rest of the problem you'd have to do by actually putting in a joint PDF, f of x, y. But it's then just calculus from here on out. We also learned last class when you have a joint PDF, you can find the individual PDFs for x and y, and we call these marginal PDFs, just like for PMFs, we had marginal PMFs for x and y. Each of these just tells us what the distribution is for x and for y, and but it loses um, the joint property of how the two random variables are connected to each other. In any case, the way to think about this joint PDF is to think about you have a joint PDF defined on the plane. And what this line integral is doing is for a particular value of x. Essentially, it's adding up all of the probability, uh, along this line. And that's giving you the density function for x. And the same thing applies for random variable y. And in this case, we fix a value of y. And what this integral is doing is now all integrating over all possible x's. And it's integrating this joint PDF over this pink line. And the result is you get the density function for just random variable y. Finally, we ended last class with a definition for random variables x and y independent. And in this case, we really had two definitions, one for the discrete case and one for the continuous case. So in the discrete case, we had that the joint PMF factors into a product of marginal PMFs. And in the continuous case, we had essentially the same thing, that the joint PDF factors into the products of marginal PDFs. And this factorization in both cases has to be true not just for some x and some y, but it has to be true for every x and every y. For discrete random variables, the condition reduces to the probability x equals x and y equals y. This joint event has to factor into the probability x equals x times the probability y equals y. That's precisely what factorization of the joint PMF tells us. And this is equivalent to the events x equals little x and y equals little y are independent events for all x and y. So learning what the value of x is gives you no clue about what the value of y is. It doesn't change your notion of what the probability of y is. For continuous random variables, it's instructive to take the definition and multiply by dx dy. And then to kind of look at this more carefully and say, well, this is the PDF of x times dx times the PDF of y times dy. Over here on the left side, we really have the probability that x is between x and x plus dx, and y between y plus dy. And over here on the right-hand side, we have the probability that x is between x plus dx. That's what this marginal PDF times dx tells us, times the probability that y is between y plus dy. And so we see, in fact, we have exactly the same kind of equality in the sense that events that x is right around x within some little dx, and the event that these are independent. And once again, this has to be true for all x, little x, and all little y. So this next example is fundamental to the design of all communication systems. So we have an information signal x, and it's Gaussian with zero mean and variance standard deviation sigma x. And this corresponds to an information signal that's transmitted by a base station radio. And your cell phone has a radio, and it recovers y, which is equal to x plus z. And x is the signal, and z is a noise. This noise is Gaussian with zero mean and standard deviation sigma z, right? But the key thing is that the noise is generated inside your receiver. So in fact, it has to do with the electrons inside your amplification circuit bouncing around. And most importantly, this noise has nothing to do with the information signal that the base station is transmitting to your phone. So the model for this system is that that X and Z, the signal and the noise, are independent, and independence implies that the joint PDF of X and Z is equal to the PDF of X times the PDF of Z. And in fact, we can simply write down what these are. This is 1 over square root 2 pi sigma x e to the minus x squared over 2 sigma x squared times 1 over square root 2 pi sigma z squared e to the minus z squared over 2 sigma z squared. Okay, and this slide just repeats what we just derived. So here's a pretty good problem to exercise our new definitions. So we have random variables x1 and x2, and they are independent and identically distributed. Each one has a PDF given by fx of x. So as a comment, the words independent and identically distributed come up so often that in fact we give them a name, and the name is IID, independent and identically distributed. I'll often just write IID as if it were a word because it's so convenient to use. So the fact that they're identically distributed means that x1 has a PDF, fx1 of x. It's exactly the same function as fx of x. And that in fact is the same as the PDF of x2 with dummy variable x. So this problem is actually an old exam problem from years ago, and you can kind of tell because in fact the steps get progressively more difficult. The first step is something you could have solved in the previous chapter. It just asks you, what is the CDF of x, which could be x1 or x2? The second step is a little harder. It asks you to calculate a probability, a joint probability of x1 and x2, each being less than or equal to 1. The next step generalizes the previous step by asking you about a random variable w, which is the max of the two. And we'll see that the calculation of what is the CDF of w at 1 is essentially the same as in part B. And then finally, the fourth step, and that's the kind of thing you do if this were on an exam and you're planning on getting an A, is to be able to, in general, find the CDF of W. Okay, so let's start with part A. We know that the CDF of x is the integral from minus infinity to x of the PDF integrated using a dummy variable u. Graphically, what's happening here is that as a function of the dummy variable u, we have a PDF of x goes from 0 to 2, and at 2, the height is equal to 1/4. And now what this integral says is that if we choose some particular value x, the CDF is the area under the curve up to that x. So it's this area. So when x is less than 0, in fact, that area is 0. And when x is between 0 and 2, this integral becomes the integral from 0 to x u over 2 du, which is equal to u squared over 4 from 0 to x. And the answer is x squared over 4. And finally, for x greater than 2, the CDF of x is the integral minus infinity to x, fx of u du. And I've switched to redding because an x that's greater than 2 we can mark over here in redding. And in this case, this PDF is 0 for x less than 0, but it's also 0 for u greater than 2. So in fact, what we obtain is this is the integral from 0 to 2 times u over 2 du. And if we want it to be really clear, there's also an integral from 2 to x, but the CDF is 0 over that interval, so it's 0 du. So this integral is 0, and we get u squared over 4, 0 to 2, and that's equal to 1, exactly as we would expect, because the random variable x is always less than or equal to 2. So to summarize, the CDF of x is x of x, and it's equal to 0 for x less than 0. It's equal to x squared over 4, 0 less than or equal to x, less than or equal to 2, and it's equal to 1 for x greater than 2. And this is the answer for part A. Now for part B, we're asked a question about the pair of random variables x1 and x2. Specifically, we're asked what is the probability x1 is less than or equal to 1 and x2 is less than or equal to 1. And this problem is more complicated because in fact the probability is defined on the two-dimensional plane with respect to x1 and x2. And we have two conditions that have to be met. One condition is that x2 has to be less than or equal to 1. That means x2 is below this line. And x1 has to be less than or equal to 1, which means that x1 is to the left of this line. And it says we have to be in this region. Now, the thing that we've kind of omitted here is that this is a generic picture for every x1 and x2. So you can write this still generically as equal to the integral from minus infinity to to 1 minus infinity to 1 of the joint PDF of x1 and x2 dx1 dx2. So this expression of x1 less than or equal to 1, x2 less than or equal to 1 is generically true for every pair of random variables x1 and x2. In our specific problem, though, we know that x1 has PDF, which is identical to the PDF of x2, which is equal to x over 2, 0 less than or equal to x less than or equal to 2, and 0 otherwise. And now we have to use the fact that x1 and x2 are independent. So independence tells us that the joint PDF of x1 and x2 is equal to the product of the PDFs. And now conceptually, the way we think about this is that we have now this x1, x2 region, and what we can do is we'll observe x1 is between 0 and 2, and x2 is between 0 and 2. And so there's a box of possible x1s and x2s. And in that box, the joint CDF of x1 and x2 is equal to the product of these individual CDFs. And that's equal to x1 over 2, x2 over 2. It's equal to x1, x2 over 4. And if you're a fan of calculus, you can finish the problem by doing this integral. So the probability that x1 is less than or equal to 1, x2 is less than or equal to 1, is the integral over this region, because it's the intersection of where the joint PDF is non-zero and where the condition x1 less than or equal to 1 and x2 less than or equal to 1 is met. And so this integral is 0 to 1, 0 to 1. And now we plug in the joint PDF, dx1, dx2, and this becomes, these integrals separate x1 over, we'll put the 1/4 out front, x1 dx1, 0 to 1, x2 dx2, and we get 1/4 of x1 squared over 2 from 0 to 1 times x2 squared over 2, 0 to 1. If we want to be careful, we could put parentheses around these. And so this is equal to 1/4 times 1/2 minus 0 times 1/2 minus 0. And so the answer is 1/4 times 1/4 is 1/16. On the other hand, maybe you're not a calculus fan. If you're a fan of probability, you'll be like, oh, we ended up duplicating these two integrals because in fact x1 and x2 are independent. By independence, you could write this. x1 is less than or equal to 1, and x2 is less than or equal to 1. Well, x1 and x2 are independent, so events defined in x1 are independent of events defined in x2. And so this is the probability x1 is less than or equal to 1 times the probability x2 is less than or equal to 1. And that's really the CDF of x1 at 1 times the CDF of x2 at 1. But in fact, both of those CDFs are the CDF of x at 1. And so it's the CDF of x at 1 squared. And we found the CDF of x at 1 before. The CDF of x at 1 is equal to x squared over 4 at x equals 1, which is equal to 1/4. So putting these pieces together, we get that probably x1 is less than 1 and x2 is less than or equal to 1 is equal to 1/4 squared, 1/16. And we did it using independence and the property of the marginal CDF, or the CDF of each individual x. And we avoided doing the calculus. Either way is fine. If you like calculus, then feel free to do it that way. So now we're ready to work on part C of the problem. Part C of the problem says, let's define a random variable w, which is equal to the max of x1 and x2. If you look through the homework problems, you'll see there are a lot of problems involving maximums, and it's because they're all old exam problems, and on an exam, testing what properties the maximum of two random variables has generally makes kind of for simple exam problems that also demonstrate that you really know what's going on. So basically, I really like testing the maximum. So in this problem, we have W is the max of x1 and x2. That means if you do the experiment and you generate x1 is 33 and x2 is 87, then the maximum of 33 and 87 is 87, right? You just pick out, after you've generated both random variables, you pick out the bigger one. So now the question we're actually asked is, what is the CDF of W at 1? And so this is the probability W is less than or equal to 1. And this, because W is the max, is the probability the max of x1 and x2 is less than or equal to 1. And now here comes the kind of the big leap, which if you understand it, all of these problems with the maximum become really simple. And the big insight is that the max of x1 and x2 is less than or equal to 1 if and only if, and I'm writing this out just to be excruciatingly obvious, x1 is less than or equal to 1 and x2 is less than or equal to 1. So to see this, we can use the logic to go in both directions. For example, if the max is less than or equal to 1, then x1 is less than or equal to 1, and x2 is less than or equal to 1. And going in reverse, if you have that x1 is less than or equal to 1, and you have that x2 is less than or equal to 1, then you know that the maximum of the two random variables is less than or equal to 1. And this gives us our big insight to solving the problem. So the CDF of W is in fact, it's this probability, the probability the max is less than or equal to 1. But this is in fact exactly the probability that x1 is less than or equal to 1 and x2 is less than or equal to 1. And now, like you could do the previous steps over again, but this is precisely what we found in part B. This is equal to 1/16. So now we're ready for the final part of this problem. Part D asks you to find the CDF of random variable W. And this is a little bit tricky, but in fact it's kind of just a little bit of a generalization of part C. And the reason it is because it's the probability W is less than or equal to W, and that's the probability that the max of x1 and x2 is less than or equal to W. And now you have exactly the same logic we had before. And the logic is that the max of x1 and x2 is less than or equal to W if and only if each of the random variables is less than or equal to W. So in fact, this is the probability x1 is less than or equal to W and x2 is less than or equal to W. So it's easy to gloss over this step. It seems kind of obvious, but in fact, it's like one of those key differentiators that if you really understand how this works, then you're probably getting an A in this course. And if you don't, you're probably not. Like it really is kind of a fundamental thing we see over and over again. So working with it, we know that by independence of x1 and x2, that's going to imply that this is equal to the probability x1 is less than or equal to w times the probability x2 is less than or equal to w. And so this is the CDF of x1 at w times the CDF of x2 at w. But in fact, both of them have the same CDF. So this is the CDF of x at w, the whole thing squared. And now you go back and revisit your answer for part A, where you found out the CDF of each of these x's, x1 or x2, is equal to 0 for x less than 0, x squared over 4 for 0 less than or equal to x less than or equal to 2, and 1 for x greater than 2. And so in fact, we could, just to be completely clear, in terms of w, we have exactly the same thing, but with w replacing x, it's just a dummy variable. And so this expression over here, the CDF squared, we just have to square the CDF for each term in the expression. So it's 0 for w less than 0. And it's w squared over 4, the whole thing squared, for 0 less than or equal to w less than or equal to 2. And it's 1 squared, which is 1, for w greater than 2. And then we just check our answer. We recall that this is equal to w4 over 16. So the next two slides have the solution from the solution manual, and you'll see it's exactly the same. So just as we said, we see here in part D, we get the solution w to the power 4 over 16. And it's kind of a nice answer, but the reason we're really doing this problem is that this is a good example of w is a function of random variables x1 and x2. And functions of random variables come up all the time. And in fact, it's the subject of the second half of this lecture.